let's do it. So I want to do some fancier Turing machines today, and really all I want to do is some examples of Turing machines, and these ones are more sophisticated than the ones from last time. Actually, the ones from last time were all regular languages that we did Turing machines for, which are, you know, fairly simple. I want to do some that are quite a bit fancier today. So let's make a Turing machine that accepts A to the n, B to the n, everybody's favorite non-regular language. Is that on the homework? I don't think so. It should not be. Did anybody see this on the homework? Maybe. I don't know. I want to talk about how you would make a Turing machine for this. Maybe that's part of the homework assignment, but it wasn't your job to make it on the homework assignment, right? Yeah. Really, this example is important to talk about because it forms like a standard type of example that we're going to do several variations on the basic strategy for this. So, the strategy, how are we going to make a Turing machine that accepts A to the n, B to the n? The idea is we start, of course, with, you know, something like A, B, B, B on the tape. And the machine has to basically go through the string and verify that there are the same amount of A's as there are B's. And then once it decides that, then it will accept. And if it gets stuck at any point, then it will reject.
So for this one, you have to go through the entire string.
You do have to go through the entire string for this one, yeah. Because there's no way to tell if it really looks like A cubed followed by B cubed unless you go all the way to the end. Yeah. If it was just a language like any string that starts with a B, then you don't have to read everything. All you have to read is the first letter. But most of the time, you're going to have to read all the letters. So you start with this on the tape, and then what is my strategy for checking if there's the same number of A's and B's? There are a lot of ways that you could think about doing this, but the way that I want to do it is a fairly general way, which can be easily adapted to build other types of Turing machines. So my strategy here is marking, and this is a common Turing machine sort of computational strategy that we're going to use. The idea is you go through the string, you mark the first A, and what I mean by mark is just change it to X to signify like I already read this one. And then you move to the right until you find a B, and you mark that also. Turn that one into an X to match off the A that you did. And then you go all the way back to the beginning, and you just continue doing that forever. All right, so you mark the first A. What I mean by mark is you change it to an X, and then mark a matching B, and then I will say go back to the beginning, and repeat. And then somehow we'll decide once we get to it. How exactly do you tell when you're done? Etc. All right? This is the general strategy though. So for example, if I were to write down, specifically for this string, AAABBB, what would the computation look like? I'm not going to write every little step, and I'm not going to write where the head is, but for AAABBB, the tape, just so that we're all clear on what this looks like, the tape looks like, you know, you start with AAABBB. After the first mark, it looks like XAABBB. And then you move over, the head would be like around the X, and then it moves to the right until it sees the B, and it marks the first B. So the next The tape will next look like this after you make the next change. And then you go back to the beginning, mark off the first A that you see. So next it will say XXA, XBB. And then you go back to the right and mark off the next B, XXA, XXB, right? This is the strategy. And then you go back to the left, mark off the first A again, XXX, XXB. Then you go back to the right and mark off the first B that you see, XXX, XXX. And now you're done. And basically the signal that you're done is that everything is at X. And that's how you know you should accept. If at any point, if there were like extra B's, then the thing wouldn't end up being all X's. And so that's how you would know you failed. If there were extra A's, then actually you would have marked off some of the A's, but you would have no B to find after you marked off some of the A's. And that's how you would know to stop. Anyway, this is the strategy. It's by marking, all right? I'm going to see if we can translate this into a Turing machine. This one is going to have some actual loops in it because it involves doing a certain number of things and then going back to the beginning and doing that whole thing again. So I'm going to try to write out some sort of steps about what we're doing and then vaguely translate this. These are going to be somewhat vague steps, which I will then translate into a Turing machine diagram. Maybe just so I can fit it all on without scrolling, I'll write it down here. So these are basic steps. Would be, first of all, mark some A, right? So think of starting at the beginning all the way to the left. You should start by marking A, and then move to the right, of course. That's sort of, I would call that step one. Step two would be move to the right until we see B, all right? And then mark the B. Actually, that's all another step. You keep on moving to the right, and actually as you're moving to the right at that point, all you're going to see is other A's that you're skipping over. And then maybe you're going to see some X's that you're skipping over, which would be previously marked B's. But in any case, you will eventually arrive at a B, and you mark that. After you do that, you want to go all the way back to the beginning, move yourself to the left, all the way to the beginning. So now move to the left until, it's convenient to write it in terms of until we see, I say move to the left all the way to the beginning. What does that mean if you want to phrase it in this way? Until you see, I'm going to go back really all the way to the first A. So I don't think it's going to be an X. Because, for example, like if I was right here, I mark this B, I would be right here. If I move to the left, I will see X's. I need to pass by that X. I also see this A, but there's no guarantee that that's the leftmost A, which is really what I want to see. I think actually you got to go all the way back to the beginning. Yeah, until you see a blank. That's all the way back to the beginning. So I'm going to see move left until we see a blank. And then you want to move to the right until you're pointing at another A, and at that point you repeat the entire procedure, all right? So I'm going to say move right until we see A. And then repeat everything, right? This is kind of like 4 different steps here that I'm going to try to translate into a diagram. And in fact, my diagram actually will only require 3 steps. I'm going to combine that one that looks like the last one here is actually easily combined with the first one in a loop. You'll see how it works out. All right, let's just see if we can draw the diagram here. I'm going to start in a starting state. And I'm going to give numbers to these states. 1, 2, 3. And like I said, the last one actually we can include in state 1 also. Anyway, in the first state, it says mark A and move to the right. Can anybody say what exactly? So this is going to be an arrow like this, which moves to state 2. How would I label that arrow? To mark A and then move to the right? Yeah?
A/X, R.
Yeah, excellent. Somebody watched the video. That means if you read an A, you change it to an X, and you move the head to the right by one position. Excellent. That's what it is. Mark the A and move to the right. All right? Okay. State 2 is move to the right over and over again until you see a B. So this, I'm going to use a loopy edge like this. This is how you get the over and over again effect. Keep on moving to the right until you see a B. When I see keep on moving until you see a B, that means if what you're seeing is A's, you should just move to the right past them. So that will look like A, A, R. Is there anything else you could see at this point? Did you want to move past?
X's.
Yeah, you could also see X's at this point, which would be previously marked B's. You still have to move to the right through those. So I'm also going to put X, X, R. That means go to the right through any A's and also through other X's. If you see a B, then you don't continue looping forever. You actually, if you see a B, you're going to go down to step 3. Any suggestion? What should I write for that arrow? This arrow is when you see a B, you should mark it and then prepare to move back to the beginning.
B/X.
Yeah. And what direction you want to move? L. Yeah. BXL. That means once you find the B, you change it to X, and then you have to move either right or left. You might as well, it doesn't matter all that much, but you might as well move left because your next step, step 3, is about moving all the way back to the beginning. Anyone want to say, how should we handle step 3? This is meant to go all the way back to the beginning until you see a blank at the beginning. Yeah? Yeah, so make a looped edge here, AAL. That means move to the left past any A's and? Yes, also X, XXL. Do I need a B, little b? I think actually at this point, I mean, it wouldn't hurt to put in there BBL, but I think actually at this point, there is no way, after you marked a B, everything to the left is always just X's and A's, so it's not necessary. And when you see a blank, that's your signal to go all the way back to the beginning of the whole procedure. And I'm going to say BBR, because when you see a blank, it means actually you've overshot the beginning of the string by one spot, and so you want to move back to the right. Now, there is this matter of what I wrote as the last step here, move to the right until you see an A. That is, after you back it up all the way to the beginning, you will see some X's, and you need to move to the right past those X's. Now, you could make a special state which does that, but actually, you can put that right here, X, X, R. That little loop never happens the first time through the machine, but in subsequent steps, it does happen. Yeah?
So to make observation, should we minimize the amount of states or the amount of states?
Yeah, he asked, should we minimize the amount of states? And the answer is, I don't care if you do that, although it's probably easier to understand if you do make a reasonably efficient type of machine. But just like for NFAs, DFAs, I typically don't care. All right? Yes?
Do you have to move left or right every time?
Yes. So part of the rules of how the machine works is you must move to the left or right. You're not allowed to just stay put. And you're not allowed to, say, jump several steps to the right or something like that. Yeah.
And then which one was one the accepting state?
Yeah, we need to talk about what is your trigger to accept the string. Actually, none of the states that are written should be an accepting state, because remember, the way a Turing machine works is if you ever reach an accepting state, everything stops and the string is accepted. But we don't actually want to stop at any of these intermediate steps. So what I'm going to do is add an accepting state into the diagram somewhere. So you have to think about at what point will you realize that the string should be accepted? At which of these steps will it happen that the string is accepted? Yeah.
It would be after you read all X's and you hit a blank.
Yeah, so it will actually be from state 1. Yeah, I think it's this is what the tape will look like. And this, if the tape does look like this, you'll be in state 1 and you will read X's all the way across until you see a blank. So if you encounter a blank in state 1, that's your That's your cue to accept. And so I'm just going to add in, sorry, I didn't really leave a good amount of space for that. I will say blank. I guess I'll just say BBR, although that is mostly irrelevant. It's just when you see a blank, it needs to go to the accepting state. The second blank and the R there don't matter. Yeah.
Would you ever replace a blank with anything?
Typically, no. I mean, you can if you want to, but if you have a very sophisticated Turing machine, you can do things like, while you're reading the input string on part of the tape, you can store some memory on another part of the tape. I mean, that's allowed, right? And if you want to do that, you have to write new stuff into some other part of the tape, which would involve changing blanks into actual letters. But we're not typically going to do that. All right, this is not terribly difficult example, I suppose. Although the concept of marking off letters is super powerful. We do this kind of strategy all the time in making Turing machines for various things. I wanted to just make sure that everybody is with it enough to write derivations. So this is pretty easy, but let's show that AABB is accepted. On this Turing machine. Remember, the way that we write these derivations is, a little confusing maybe. It's not terribly confusing. You write down just the state of what the whole machine looks like in every step. So the machine begins like this: B1 AABB blank. Blank 1 AABB blank. What that means is, what you're writing in each of these steps is basically the contents of the tape. That 1 there indicates that the head is in state 1 and it's pointing at the first A. And these blanks on the beginning and the end indicate that there are actually infinitely many blanks in either direction, because the tape begins with infinitely many blanks stretching out forever to the left and to the right. All right, and then I'm going to write this. This fancy little arrow is the way that they write it in our book. If you want to write it slightly differently than this, that's fine, although I'm always going to write it this way. What does it look like next? You just have to say, what happens actually if I'm in state 1 and I'm reading an A? You look on the diagram. It goes to state 2, changes the A to an X, and moves the head to the right by 1. So the effect will be, I still have blank, and now that A turned into an X, and the head moved to the right by 1 position, and now the head is in state 2, and now I'm looking at A, B, B, blank. That's the instantaneous description of the Turing machine after that. The number represents the state of the head, and the location of the number is what letter it's pointed at. So the 1 there changed the first A into an X and moved to the right. Okay, now I have state 2, reading an A, it says AAR, so the 2 is just going to move to the right, leaving everything else the same. It will say BXA2, B blank. Sorry, I try not to say B when I mean blank. It looks like a B though. All right, next I have 2 reading a B. That will be in state 2 here. Read a B, you do this arrow, BXL. And so this B turns into an X, and then the state moves to the left and it becomes a state 3. So now I say blank X 3A X B blank. It's pretty cryptic the way we have to write this, but it'll make you look cool in the club. They will say, wow, you really understand all that? You say, yeah, kind of. All right. Up to you how much you want to impress them. Okay, 3A. I'm in state 3, reading an A. I do this arrow, which is AAL, so it just moves to the left, keeping everything on the tape the same. So it now says blank 3XAXB blank. All right? Now I have...
Where do you place the like 2, 1, 2, 3? So in our last second, where do you place 3? Like before or after what? Yeah, that 3.
You mean why is it right there?
Yeah.
So this 2 in front of the B means the head is in state 2 and it's looking at this B. We always write the state right before the letter that it's pointing at. This is a little confusing, I know. And so since this 2 moved to the left and turned into a 3, now the 3 is in front of the A. All right, anyway, I'm looking at blank 3x. 3x, in state 3, when you see x, it goes XXL, not my t-shirt size. So and then the 3 moves to the left and remains a 3. So now it says, I guess, blank 3, blank x, a, x, b, blank. That first blank that I wrote there is like a new blank, but it was always there before, I just didn't write it before. The 3 is now pointed at a blank, and now I'm going to do this arrow here back to state 1. So now it says blank 1 x a x b blank. And now we've done one full sort of iteration through that triangular loop. In terms of writing the derivation, we are now halfway done because we went through once. It's going to now go through once again. All right, so state 1, seeing an x, will just move to the right and stay in state 1. Sorry, I'm going to have to zoom out again a little bit to hold it together. It'll say blank x, 1, a, x, b, blank. Next, state 1, reading an a, does that arrow AXR. So that a turns into a x. It moves to the right and goes to state 2. So it's going to be blank x, x, 2, x, b, blank. I think I did that right. All right, now I'm in state 2, seeing an x. It should stay in state 2 and move to the right. So blank x, 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 2, b, blank. State 2, reading a b, I do this BXL arrow. That b turns into an x, move to the right, and move to state 3. So it's now blank x, x, 3x, x, blank. The 2 moved to the left one position, and the b turned into an x. State 3 with x's will continue to move to the left. So one time to the left, it's blank x, 3x, x, x, blank. One more time to the left, blank 3x, x, 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 blank. And one more time to the left. Sorry, I don't know if I can hold this all together. It keeps getting smaller. 3, blank. I should put another blank there. X, 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 blank. Right? 3, looking at blank, does a BBR back to state 1. So this is now blank 1 x, 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 blank. And then state 1 does this loop XXR. So it's going to do 4 times, just moving the 1 to the right each time. I don't need the picture anymore. Blank x1 x, 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 blank. That was once to the right. Do it again. XX1 x, x, blank. Again, blank x, x, x1 x, blank. Again, blank x, 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 x1 blank. And now finally, in state 1, we see blank, which moves us into the accepting state. I will just say accept with an exclamation. All right. So usually we are not going to write out derivations like this just because there's a lot. It's kind of a bit much. But if you really wanted to write it out, that's what it looks like. All right. Any questions about all that? This is like Hollywood mathematics. This is the kind of thing that people like to see. Just a whole bunch of nonsense with a few weird-looking arrows in it. All right. I would like to do some simple modifications. I got one simple modification, and then I have one for you all to try. Let's try a to the n, b to the 2n. All right, this one has basically double b's. Anybody would? So my strategy for this one, remember, was you mark off one of the a's, then you run down the string and mark off one of the b's, and you run back to the beginning and do that all again. Anyone want to suggest, just in simple words, a variation? Yeah.
Well, when you get to the spot where you mark a B, I guess you could move right, and then the next step mark a second.
Yeah. So my strategy this time will be mark A, and then move right, and then mark a B, then mark another B, and then move back to the left, and do that over and over again. This is very similar strategy. Rather than write out the steps in words, would you mind if I think we can just kind of try and make this happen. So from state 1 is my starting state. You should be inspired by the diagram that we wrote before, and I think, as much as you can, try to copy that picture. You may have to insert some extra stuff. Well, you definitely have to insert some extra stuff at some point, but I don't think right now is that point. I think in state 1, we still want this XXR, which was in state 1 before. This is not used the first time through, but this is used on subsequent iterations. The beginning of the string will have turned into some x's, and you want to blow past those x's at the beginning if they exist. Once you see A, you should mark it and move to another state. So we want to do AXR like that. I'll call this state 2, although the names of the states are not really important because I'm not going to try to draw a derivation this time. What do we do in state 2? We want to move to the right continually through a bunch of other A's and possibly X's until you see a B. So this state is going to have a looped edge, AAR, XXR, right? We are moving through other A's, which we don't want to mark in this step, and also moving through some X's, which represent previously marked B's. And when you see a B, you exit, right? BX. Now, in the old version of this machine, it said BXL. I don't think we want to do that L, because our goal here is actually to mark off 2 different B's. So I'm going to say BXR instead. You mark that first B. I'll call this state 3, I guess. And now, in our previous machine, this state, it did some stuff, but also basically went back to the first state, right? But I don't think that's appropriate. Anyone have a different suggestion here? Yeah?
Do BXL, do another state.
Yes, basically another BXR, but this time actually it can be BXL because, and then into another state, BXL. That's the second B that's getting marked. And then this other state will behave like state 3 did in the first example. So this state 4 will move to the left over and over again until we hit a blank. So this one goes XXL, AAL. Again, you could put BBL here, but it's not necessary because at this point of the computation, it's not going to pass any little b's. And then when you go all the way back to the left, you will encounter a blank, and that is when you want to go back to the first state and loop everything. I'll say BBR. That's when you got all the way back to the leftmost end of the string. And there's one last thing to add in there. Yeah, the accepting state, but this works exactly the same way. If in state 1, you're doing that XXR and you actually run yourself all the way to the end, then it should be accepted. So I do like this. BBR or whatever, blank blank R. Only that first blank there matters. The rest of it could be anything. All right, great. Any thoughts about that one? I got one for you all to try. Can you all try? This again is a simple variation on those machines. let's try a to the 2n, b to the 3n. The basic idea here is in each iteration, you want to mark 2 a's and 3 b's, right? Because that's what you want here. 2 a's go with 3 b's. See if you can do it. Thank you. Good start. Ordinarily, you don't have to give the states numbers if you don't want to. I only did it that time just because I knew I was going to do a derivation, but it's usually not important to give the names.
Can you do something like this?
Mm-hmm. Yeah.
Okay.
Yeah. Somewhere you should have to make it start. Right over my head.
Oh, yeah.
Actually, you should have.
Yeah, I have that.
Mm-hmm. I'm going to try and start writing mine. All right, are we ready to talk about it? You basically take what we just did, but insert another, that's not right, is it? I need another B. Sorry, I'm missing a, BXR. 2 A's match with 3 B's. BXR, BXL, and then this is blank, blank R. This, my accepting state. Like that. I think that'll do it. Anybody agree or disagree? Yes, great. It's just like the one we had before, only you have 2 marked A's matching with 3 marked B's in each iteration. All right, great. I hope you feel good about that. I had one more example to do, maybe two if we have time. This is a particularly interesting example. How about a Turing machine for matched brackets? Matched brackets. You into matched brackets? This is just a string where the alphabet, in this case, is going to be that and that. So the alphabet characters are just the left bracket and the right bracket. I know that's a confusing bunch of nonsensical symbols there. I'm saying the alphabet letters are just the left bracket and the right bracket. And it accepts a string made up of brackets. Come on now. Except if the brackets match up. Appropriately. So, for example, this is accepted, right? Because those brackets are actually balanced appropriately. Whereas this is rejected, right? Because, well, there isn't even the correct number of left and right brackets, but also something like maybe that is also rejected. That one has the correct number of them, but they're not arranged properly because I see a bracket on the right which has no match on the left. All right. That's what I want. A Turing machine which reads a string like that of brackets in some arrangement and accepts if the brackets are actually properly balanced and rejects if they're not. All right. This one actually, I'm going to use a marking off trick to match off, the brackets sort of in pairs. And by the time we get to the end, hopefully everything will have been marked off, which would be, turn into an X. This is actually a little tricky though. So we'll do it by marking. But check it out. If I have a string of brackets like this, say, I think that this one actually matches. The idea would be, think about how the machine is supposed to handle this. I start, on the leftmost thing, mark this one off, and then you go down the list here and find the one that it matches with and mark that one off. The question is, how do you know which one it matches? If I'm here, which one actually matches this one? Yeah.
You would just go to the outermost one, right? Like for the.
In this example, this one matches the one at the very end. Yeah, it does not match this one here. You might be fooled by this one. So you might think, all right, go all the way to the end and then pick up the last one there. But check this out. How do you like that? In this one, the first one matches that one. It doesn't match the one on the end. So how are you going to tell which one it matches? You're not allowed to say something like, you count up as you go. I don't want to count as I go.
I feel like there's something to do with like the braces are like opposite each other. Or there's a blank on the other side.
You mean like when you see that,
Yeah.
that means something? Maybe. There's actually a very cute, simple trick that makes this easy. You got an idea?
You basically, I would call it outline closure. You go through all the outline, and then you go through all the flows. You stop at the next outline only.
Okay. This is a good idea. He said something like, go through all of the, I'm not sure I fully understood. Go through all of them and then start somewhere else. Actually, the key insight is you should not start at the beginning. It turns out, this is I'm still kind of mystified by this. This is very cute, but start with the rightmost we start with the rightmost bracket that looks like that. And then everything is great. And this, we move to the left and match with the nearest bracket like that. This is the cute trick. It only works if you start at the end and move back to the left. Very strange, but true. Yeah.
So, I guess, like, wouldn't that just be the same issue but in reverse? Like, I know this works, but like, I don't know. Like, I feel like
It sounds like it would just make the same problem, but in reverse, like, you know what I mean?
Sorry, this is not correct what I just wrote there. Yeah. What I wrote here is just completely symmetric to what I said before and is not any different. What I meant is this is the trick. You start with the leftmost close bracket and you match that with the nearest one to the left of that. Let's just demonstrate on a string. For example, if I have this, all right, this one is correctly balanced. Let's try and follow what I said. Start with the leftmost right bracket. That's this one. Mark that. And now move to the left and match that with the nearest left bracket, which would be this one right there, immediately next to it. This strategy is guaranteed that you will actually match one with the proper other one. In my opinion, it's very weird that this works, but it does. All right, and now from there, you again start with the leftmost ending bracket, which in this picture at this point would be this one here. And I mark it, so it will say XX bracket X, like that, and then move to the left from there and match the nearest open bracket, which looks like this. And then you start again. You start with the leftmost closing bracket, which is this one here. XX, XXX. And then from there, you move left and match it with this one. And then we start on the end and then match it with the one on the beginning. This is what this is not actually the full derivation, but it is what the tape looks like from one big step to the next, like that. All right? That's the strategy. Actually, this you can write very simply as a Turing machine. It only requires 3 states, really. We got 5 minutes. That's enough time. So, starting in my starting state, what can anyone describe in words? What's your first order of business? If you start, as always, you start on the far left of the string. What should I be doing first as a goal? Yeah.
Move that and move right. Oh, yeah.
Yeah.
Move right.
Move to the right over and over until what?
Until you get to the other way, and then.
Yeah, you should move to the right until you see a closing bracket, right? Because the whole strategy said you begin with the leftmost closing bracket. So starting from the beginning, you loop to the right like that. Open bracket R. That means I'm just moving right past any open brackets that I see at the beginning of the string. Do I need to also move past X's at this point? I think I do. Like at the first time through, there's not going to be any X's, but in later steps, you will have to start at the left side and move past some X's before you see a closing bracket. So I'm also going to put an XXR here. And then when you do see a closing bracket, you exit, and then you start moving back to the left. All right? And from that new state that I just drew, we need to continue moving to the left until we see a matching opening bracket. As we're moving to the left, we might go through some X's, but I think we will not go through anything else, right? It can only be X's that you're moving past here. So I'm going to do this, XXL. This is the step in which I just marked off something like right here. I just marked off one of the right-hand brackets, and then I have to move back to the left through some X's perhaps until I see a left-hand bracket. And then when you do see a left-hand bracket, you exit, and then you start going back to the right again. Actually, this will work if you just do like that. Left. Sorry, my drawing. Left bracket, X, R. That's because I just say change a right bracket to X, then I go to the left over and over again until I see a new left bracket, change that to X, and then my next step will be start again. Move to the right until you see a closing bracket again. All right? Is that it? No, that can't be it. Although you should start thinking at this point about adding an accepting state in. I mean, I would say this is basically it. That's the whole general algorithm that I described is right there. What are your thoughts about if this string is actually accepted, when will you finally notice? Yeah.
Like the other one, when it's all X's and there's a blank.
Right. When you get to all X's at some point, you have to think that will be, you'll sort of notice that when you encounter a blank after running through a bunch of X's, right?
The first step.
Yeah, I think in the first state, if you are searching for your next rightmost bracket, but all you see is X's all the way to the end. Actually, there's one little technicality. What if somehow there were a bunch of extra opening brackets here? You might be fooled into thinking you were done if you run through in this first state. If you run all the way to the left through X's and hit a blank, you might think I should be accepted, but actually it should not be accepted because of those extra guys at the beginning. So we require one little cute little thing at the end. I'm going to try and write in words what we have to do. At the end, run left all the way and make sure it's all X's. Right? You don't want extra leftover, extra left brackets. Yeah.
And that's because you could end in the middle of the string, right?
Yeah, because this Turing machine, when it finally, well, really it's because you could end. I think you could end in the middle of the string. That's true. In this particular example, actually, I sort of ended my marking offs at the leftmost side, but I never actually checked if this really was the leftmost side. So anyway, what you have to do at the end is, if you run all the way to the end and it's a blank, that's not necessarily accepted yet. You must run again back all the way through the string and make sure that it's all X's. So what that looks like is BBL here. If you're in the first state and you read a blank, that means you went to the right through all X's. Now you have to go back to the left and make sure that they're still all X's. So I'm going to put one last little sort of verification here. I'm going to do looping XXL, and if I see a blank after that, then it really is accepted.
Can you just go off the second state?
From here, I think if, and then only go to the left, you mean? I think then you will not notice if there were extra right brackets. Yeah, you have to at some point run all the way through to the left and also to the right to make sure that it's good. So this is a little confusing, but all this business here is what's accomplished by that state right there. Yes?
Why do you need that intermediate state?
before the, why can't you just end it at, with blank out?
Just accepting right here?
Yeah, why do you, that, yeah, sorry, so.
It's because we need to run through the whole string going to the left to make sure that there were no extra brackets left over on the beginning.
But if we have blanks, it's already, yeah.
Yes, but this blank occurs after moving all the way to the right. So you went to the end on the right. You have to also make sure that you get blanks on the left.
Can we do this on stack machine?
I believe this language is context-free, so the answer is yes. Although I wouldn't want to make a stack machine to do this, I would make a grammar. I think it's not so hard to make a grammar for this, and then make a stack machine. All right. See you tomorrow. Do the homework.